I'll switch no problem. நீங்க அது பாருங்க. I'll switch. Okay, so you have calculated, right? Okay, then calculate now if a light is travel to 10 minutes.
1 minute you got the answer, right? Multiplied by 10.
Okay, that's nice. Okay, if a light is traveling to 1 hour,
60 minutes.
60 minutes.
80,000? Crores. 1 second. How many seconds? 1 hour.
1 hour? That's all. That's all. Calculate. Okay, maybe you can tell like the number first digit followed by how many digits or how many numbers? How many zeros? Yes, 10 crore 800 kilometers. Okay, so that's nice. Very good. So what it means, if we are traveling in a speed of light, how many kilometers we have to travel? Within a second we have to reach 3 lakhs kilometers, right? So in a light speed, if we have traveled 1 hour, how many kilometers we have to reach? We would have to reach. It's around 10 crore kilometers, right? So that's far. So that is why we are using light as a measurement tool to measure the distance, because our universe is so vast. So we have to use alternate tool, because we can't take our meter scale to measure the universe. Some 10 meters, 20 meters, we can't do that. So we need an alternate tool. That's why we have used light as a tool to measure the distance of the universe, right? Okay. So if our light is traveling to 1 year, it will reach certain kilometers. That is called light year. Okay. So now the Hubble Space Telescope, it took the picture of the universe, which is very deep. It took a picture of some galaxy, some distant galaxy. The distance between the galaxy and Earth is around 13 billion light years. 13 billion light years. See, light years itself, one light year itself, some crores of kilometers, right? So some galaxies are far away from Earth, so which is distant, like 13 billion light years.
Thousands of crores.
Yes, thousands of crores away from Earth. Our space-based telescopes are sensitive enough to take those pictures. Okay, so the Hubble Space Telescope.
Sorry.
Yeah.
So you mean that picture that the telescopes are taking, they're actually taking it from that crores of kilometers away?
Yes. Yes. So those objects are crores of kilometers away. They are emitting some signal. Our telescopes are sensing that. Okay.
So
the
that
beauty
signal is light only.
Yes, light.
Not sound. Light.
Okay. The beauty is the Hubble Space Telescope, not the James Webb Telescope. The Hubble Space Telescope. The Hubble Space Telescope is sensitive to visible light, not an infrared. Okay. Our universe have emitting. The universe objects, the distant galaxies, other objects are emitting in a wavelength of infrared. Okay, so many objects are emitting in an infrared scale, but in the ground-based telescopes we can't receive, because our atmosphere itself is filtering the infrared rays. So people now send the very sophisticated big telescope to the space to sense the infrared signal. Okay, so this is one such telescope, James Webb Space Telescope, to the space, observe infrared signal. Okay, next slide. Yes, both. Okay, so when it has launched, so this space-based telescope launched last December 2021, And where it from launched? It launched from French Guiana. So French Guiana is a country name. This is one location in Latin America. So did you hear this name, French Guiana? No? Okay. Maybe. Okay. So maybe you can search where it's French Guiana. If you have a world map, you can try to find where is French Guiana, which is in the Latin America, Southern America, right? Southern America continent. So where you can see the French Guiana. Okay. So people have used Ariane 5 rocket to launch this space telescope. James Webb Space Telescope launched by Ariane 5 rocket from French Guiana on December 2021. Okay. So where it is, the James Webb Telescope we launched to space. Where it is? Is it very close to Earth or far away from Earth? Okay. Yeah. Somebody is telling something. Yeah.
It is near to Earth.
Near to Earth. Okay. So that's a good answer. But the space-based telescopes are not very close to Earth. It's somehow far. Where it is. Okay. So now you can play a quick game, maybe one small activity. Can I have a paper? No. Okay. Okay. Thanks. Okay, so I will just draw a few dots. You have to connect those dots. Okay, so I'm putting one dot here. Can you see this one? So I'm putting one dot here. So this is, consider this is dot because you have to see, right? That's why it's putting. Can you see this dot kind of thing? So this is sun. Let's say this is sun. Okay, and our Earth is here. Let's say our Earth is here. This is Earth. Okay. Okay, Earth is here. Okay. So what Earth will do? Earth will revolve around the sun, right? So revolve around the sun. Okay. So Earth is here. Now we need to identify few stable points. Few stable points present. Okay, so this is nothing but a tug of war. Okay, tug of war. Have you heard this word tug of war game? Yeah, one team will pull this side, another team will pull that side, right? Similarly, some tug of war game is happening regularly, simultaneously. Still now also it's happening between Earth and Sun. Okay, so what it will do? Here the sun is attracting the Earth, but the Earth is somehow trying to get away from the sun. Okay, so this tug of war is constantly happening, but some object will get locked in some points. So this is one point, this is another point. Similarly, there is one more point here and one more point is here. Sorry, not here, not this location, in this location. Okay. So there are 5 points, 1, 2, 3, 4 and one more point should come. Oh, okay, I just lost the one more point. Okay, so right now we have directed 4 points. In this 4 points, if we fix the person or if we fix the object, it won't get attracted by Earth or Sun. No object will get attracted. Attract those objects. Okay, these points are called gravitationally locked points. What? Gravitationally locked points. Okay, in physics we will call these points as Lagrangian point. Okay, Lagrangian is a scientist who discovered those points are alive in space. So that's why we call those points as a Lagrangian points. Okay, so this James Webb Telescope right now in this position. Okay, this is L2 point. Okay, so this is L2 point, L2 Lagrangian point, let's say. Okay, in this position we have fixed our James Webb Telescope to observe the sky, observe the universe. Why we have fixed L2 point? Because it's not close to sun, also it's far away from Earth, around some lakhs of kilometers away from Earth. Okay, it's not a very close to Earth, let's say some 1000 kilometers or 2000 kilometers. It's around some lakhs of kilometers away from Earth. Okay, so we will, thank you, thanks. Okay, so those objects are, these telescopes, space-based telescopes will not affected by light pollution or affected by sun, but it can receive signal from the space. Okay, So next slide. Yeah. So I told the infrared, right? What is infrared? We will try to understand what is infrared. You can see this. Have you seen something like this in some thermal camera? Yes, some TV channel. Maybe you have to use to edit. In COVID time, so many people use this thermal screening method to see people. Whoever is having a higher temperature, we can use this thermal cam to get the information about it, right? So this thermal camera is nothing but an infrared camera. So this infrared is nothing but which will sense high temperature, right? Okay. So similarly, the space-based telescope observing the universe in the like a thermal screening method. So the James Webb telescope is what it's going to do? It will thermally screen the universe. It's going to screen the universe in a thermal way, right? So this telescope, the James Webb telescope. See, this picture is, you are seeing this picture, right? This is a visible light picture. We can easily see the picture. Some flower is there, some grassland is here. So this is a visible picture. But using the thermal cam, we can't see anything. We can only sense the temperature. We can only sense where is higher temperature, where is the temperature, let's say temperature gradient. Higher temperature, lower temperature. So those are the red color patches are there, no? So they are the higher temperature area. So the blue areas are comparatively lower temperature area. So our James Webb telescope going to sense the universe in this range. Okay, in the infrared way, it will going to sense the universe. So then, how image will be look like? So those images, the James Webb telescope are going to send, right? So there will be like some darker patches will be there. So those darker patches, like they are in high temperature. Some lighter patches will be there. So they are relatively some colder location in the universe. We can compare it. There are few other instruments in the telescope itself. It will observe it will take some spectroscopic signatures of the universe and many things it will do. Okay. So our telescope, the James Webb telescope. I told you, right? This telescope, let's say, just 10 meter in the mirror size. This telescope, the amateur level telescope which we have here, it's just 10 centimeter in the diameter. So I am saying the diameter. So this diameter is just 10 centimeter, even less than a 10 centimeter. That's all. But our James Webb telescope is having a mirror with 6.5 meters in a diameter. So the James Webb telescope mirror diameter is, primary mirror diameter is 6.5 meters. So that's very big. We sent that much big instrument to the space. Okay, the Ariane 5 rocket is right. So that is a one such sophisticated launch vehicle we have in the world to launch very heavyweight instruments to the space. Okay, so this is very big telescope, 6.5 meter long, and which has 80 segments. The telescope is we didn't send a whole 6-point mirror itself. We sent in a folded way. You know origami, right? You know origami. Origami is a folding way of paper and making some good toy kind of structure. Similarly, in a James Webb telescope, we have folded the mirror in multiple steps and we packed in a rocket, Ariane 5 rocket, which launched to space, and where we have unfolded. Okay, and maybe later this presentation I will show the video how the James Webb telescope have unfolded, how it's folded and how it's unfolded. We will see that. Okay, next. Okay, so this is the James Webb. Actually, this telescope was named initially as Next Generation Space Telescope. So initial name was Next Generation Space Telescope. See, you know, when this telescope commissioned, so commissioned in the sense somebody have to propose this project to the space agency. Like maybe we can propose some space projects to ISRO. They will call this as commission. Once they have approved, they will call this project as commission. Okay. Similarly, this James Webb telescope commissioned in 1990s. Not today. 1990s. Okay. Almost we took 20-30 years to get ready with this telescope and we fixed its position. Okay, it was so amazing one because it needs so much of amount and so much of instruments, technical support, even precision level. Measurement should be precise because that much amount we are spending. We should have received a very quality image, right? Quality information. We are not we can send some instrument to space and whatever the signal is receiving, that's enough. We are not like that. The scientists are not like that. We need a very sophisticated instrument to get very precise signal of the universe. That's why we spent some 30 years to build the instrument and we launched. Okay. So this one gentleman, actually his name is James E. Webb. His name is James E. Webb. He commissioned and he proposed NASA we have to build such next generation space telescope to observe the universe. So in 2022 September, the commission people have renamed this telescope as James Webb Telescope. Initially, this telescope name was Next Generation Space Telescope. Okay, yeah, next one. Okay, who are all involved in this project? So ISRO is not involved, but anyway, so many scientists from India are going to benefit out of this space-based telescope because we can receive signal. Still, this is open for human community, right? Humankind. We are searching our origin, how we have came to Earth. We don't know. We are made up of stardust. Literally, we are made up of stardust. Then people are searching how the life has originated in the Earth. So we are searching that. That's why all the humankind in the Earth can use the information of James Webb Telescope. So this is one very big milestone of humankind to observe the universe, to deduct research about the universe. Okay. So these are the three primary organizations. One is Canadian Space Agency and NASA. You know, we are going to live stream it in another 30 minutes. Let's say even in 20 minutes. So NASA is here and ESA, European Space Agency. These are the three primary organizations who have funded and collaborated and they built this telescope. They have developed this telescope.
And they're all into space research.
Yes, they are into space research. There are many space agencies around the world. One in India, we have Indian Space Research Organization. One in Japan Space Agency, and even in UAE, Dubai, we have another space agency. And even Australia has very big space agencies. There are many countries nowadays developing a space agencies. So in space domain, surely in next 5 years, let's say next even 2-3 years, the space domain going to boom like anything, and so many job opportunities will be there. So when you are into a higher education, you may get to know about various space related career opportunities. Even in computer science, physics, chemistry, even biology. We are searching about astrobiological signatures, biosignatures from the universe. So astrobiology is another domain going to evolve. So many researches going to happen. Okay, and in next 2-3 years, and it will go long. And these are the two primary institutions. And down you can see Northrop Grumman. So this is one industry. They have developed the sun shield. I will show the picture of James Webb Telescope. You can see the sun shield because it's in the space. It should not affected by the sun's heat. So sun will emit the heat, right? Temperature, right? So it should not affect the telescope. We need our telescope to be safe, right? So that's why we build a sun shield kind of structure. I'll show the picture. This industry, Northrop Grumman, so they built that sun shield structure. See how big this sun shield is. Have you seen the tennis ball ground, right? Tennis court. So that much big. One sun shield is that much big. Really, it's big. Okay, you can imagine that. And the last institution, Space Telescope Science Institute. This is a research institution going to operate, going to handle all the data and everything by this STSCI. So Space Telescope Science Institute is going to research about it. So these space agencies, Canadian Space Agency, NASA and ESA, European Space Agency, they have developed the instrument and launched to space. This industry helped them to build the sun shield. So this Space Telescope Science Institute going to do they will handle receiving data and distributing to the people and releasing the data for research and everything they will do. Okay? Yeah. So these are the collaborating institutions, organizations around the world for the space, James Webb Space Telescope. Next. Yes. This is our telescope picture. This is the James Webb Telescope, actual James Webb Telescope. Here you can see the structure. This is actually this is the primary mirror. You can see some arrow marks going here, right? So this is the primary mirror. So this is not complete structure we sent. We folded it in a specific way and we sent it to space and it has unfolded. Right?
So I mean that structure that we see now is actually
is actually there.
Hanging in space.
Yes, hanging in space. Okay. So this is primary mirror. This is 6.5 meter. I told you, right? 6.5 meter long. This is 6.5 meter in a diameter. And this is secondary mirror and heat. This is the heat shield. You can see the big structure, right? So this is heat shield. We can see this is very small, tall kind of structure, right? But in space, the wide is around 1 tennis ground. 1 tennis ground large size, this space shield. Okay, so in the back side of primary mirror, we have scientific instruments, detectors, other cameras, and everything will be here. And we have antenna here. This antenna will transmit all these signals. Whatever scientific information recorded here, it will be transmitted through this antenna to here. Okay, so today we are going to receive one such signal. First image we will, right? Yeah, next slide. Okay, now we'll come to another activity. Okay, you all have the notebook, right? Now you can draw in front of me. Actually, this telescope has 18 segments of hexagonal structure. Okay, usually the mirror will be like the circular one, right? Why we need a hexagonal mirror? Hexagonal segments. Okay, can you draw this in the top range 3 hexagonal structure, also in the bottom 3 hexagonal structure, in the middle 4 and exact middle 5. Let's say not the 5th one is going to be here because we have a sensor here, and in this line we have 4. 1, 2, 3, 4, 5. 5 lines of hexagonal segments. Can you draw this picture?
Right?
Yeah. Try this.
Girls, if you have someone disturbing now, please can you ask your friend to get up and go also?
Try this picture. Hexagonal picture.
Space noise. You have
something. He'll close it. Own YouTube.
stop talking and write, yaar. Girls, let your hands work, not your mouth.
Okay, you just try. Meanwhile, I will check skies. If moon is visible, we will check. Yeah.
Tell me your number. No. It's a different link. Tell me your number. Eight one two three 35.
Not this one.
Yeah. No. That changed. 8. I'll send you a new one.
Okay. You done? Another picture? Yeah. Yes. James Webb Telescope. No, there are no one. It will be it will be controlled from here. So we will control how to turn, which image we need to capture. We will control from here to itself. It's a robotic one.
So you said there are 18 segments, right?
Yes.
So each segment can be controlled from here.
Yes. All these segments, the entire instrument will be controlled from here. But only one disadvantage is if something happened to the telescope, we can't go and repair. If some instrument got failed, we can't go and repair. That is why we have built so sensitive and very sophisticated, safe instruments. Because we spend so much of amount, right? We can't waste the instrument like within a week, within a month. So far the estimation of life is 15 years for this telescope. So 15 years, this telescope will be there and it will observe the images. More than 15 years, yes, it will observe, but depends. Okay? Yes, your question.
Yeah.
Anna, you told we have spent more money, Anna. How much?
It's 1,000 crores.
And it can
1,000 crores. Huh?
It can be million and crores for one rocket and something.
Yeah, including rocket and everything, it will be $1 million, let's say. So the instrument cost is around 1,000 crores. Yes, your question.
Anna, that structure you showed, Anna.
The structure?
That structure.
Yeah.
It will be hanging in the space. No?
Yes.
If you said in 15 years it will not work. No.
It will be there. It will work, but the assurance we can give some guarantee, right? Yes, this telescope will work 15 years in a perfect way.
It may work for more time.
Yes, it may work.
15 years, pakka it will work.
Yeah.
Okay. But what happens to that after? Is that your question? What happens after 15
If
years?
suppose the instrument got failed, it will be there. We can't receive anything. No. Because it's far away, right? I told you, right? The telescope is fixed in the gravitationally stable point, gravitationally locked point. So it will not attract either by sun or here.
And it can
Yes, first I will address this question and then you can ask. Yes, your question.
And if that asteroid comes and hits that, it will burn, Anna.
Yeah. So exactly, very good question. Actually, we fixed the James Webb Telescope in a particular location, right? That L2 point. Last month, one very small, tiny asteroid particle hit on that one segment of 18 segment I showed, right? You have done here. Yeah. So here we can split the segments into various categories. One segment is this. This is B segment. So this is B segment and this line is C segment and this group of categories A segment. We have categorized all the mirror segments. This B segment got affected by a small tiny particle, tiny asteroid particle. But that didn't damage the telescope. The damage is null. Still the instrument is active. Okay, yes, we have some video. Yeah. Okay. So just a minute, one quick video will watch it. The folding stuff. Yeah.
Do you want that light to be turned off or it's okay?
Actually, only this you can turn on.
Yeah.
No, it's okay. You can play. No, it will be visible. There. Yeah. The light is good enough too. The projector is good. Yeah, you can see this. Yeah, right. Yeah. Play book. Wait. Pass.
And no talking, girls, please.
Thanks. Yeah. Okay. Now,
Boys are so well behaved.
in this way, so actually, this is the way we have folded the telescope. This is folded telescope. Okay, we have folded the instrument in this manner and packed into the launch vehicle Ariane 5 telescope rocket. We have packed and launched into space. This is before deployment. Okay, this is before deployment. Yeah. So once after launching this, after 30 minutes, the solar arrays will get unfolded. Okay, these are the solar arrays. Okay, I told the sun shield, right? So it will be deployed. Now the mirror is getting elevated. The primary mirror segments. Now the sun shields, the folded sun shields are getting okay. So the sun shield, this is the sun shield. Do you know why this sun shield is looking like some kind of white or transparent color? Yeah, you can see the multiple layers, right? There are 7 layers. 7 layers of sun shield. Okay, why? Just one. Yeah, why is it like white or transparent layers? Yes.
And it will reflect the sun.
Yes, exactly. Yeah, very good. So it will reflect the sunset. It won't absorb. Right? So that's why people will say like winter time we have to wear a black color or a dark color shirts because it will absorb the light. Winter time we need a heat source, right? So that's why dark color. But in the summer time people will say like white color, whitish or very light color shirts. It will reflect light. So here the sun shield should reflect the light. It should not absorb. Right? Yeah, play with me. This is after 11 days of launch. Now you can see this. The first unfolding of primary mirror happened after 13 days. This is second unfolding. Yeah. After 29th day of unfolding, after 29th day of launch, the complete mirror get unfolded and we have the James Webb
So it
Telescope on
took
space.
1 month.
Yes, it took 1 month to get completely unfolded.
And how much time did it take to reach there?
It's around 1 month. It took 1 month to reach that L2 point and another 1 month to get unfold. Now it's trying to observe the galaxies and other deep objects. It's going to send the image to Earth. Yes.
Anna, it will be there, no, Anna?
Yes.
Why it will take 1 day to open, Anna?
1 month it took to open because we have to precisely open, right? So once the sun shield opened, we need to check whether all the sun shields, it has 7 layers, all the 7 layers open in a proper way. We have to check it, right? So in that way, all the deployment, unfolding and checking, unfolding, checking, it took 1 month.
Anna, not that, Anna. One part will take for 1 day to open.
No. It depends. See, the one thing, you just go one frame before, another frame. Yeah. Let's say this is one mirror segment. Okay, this is one segment. 3 mirror segment is here, right? Primary mirror segment. This mirror segment folded in the backward way. Now we need to send a command from here. We have to send a signal that that segment has to open. So the telescope have to receive. This is 1 lakh kilometer away from here. Our signal, whatever radio signal we are sending to the telescope, it should reach. Right? It will take its own time, and the telescope will process it. The telescope computer will process it, and it will reflect to the signal whatever we have sent, and it will get unfolded.
So that means it's taking time.
Yes.
The messages sent by us.
Yes.
The instructions that we send.
Yeah.
It takes that much time to reach there. And once that message reaches over there, then that, whatever that telescope is, it takes time, yeah. Like they can't, suddenly all the segments, it's not a flower to open up together, no. But remember, we're controlling it from here, right? We have to be very careful. Even if you have to say open 2 centimeters, you have to type open 2 centimeters. So it takes a lot of instructions from here for the message to reach there, and for that the telescope has to kind of adjust itself over there, depending on the instructions that we give. That's why it takes a lot of time.
So whatever information we are sending from here, it will take 20 hours to reach the telescope. Okay, so it will take 20 hours, and the quality checking, and whether all the instruments are unfolded in a proper way, we will check that. And everything took 1 month to unfold the complete telescope. Now it's stable and it's push. Okay? Yeah. So this is the unfolding video. We saw this. Okay? Yeah. Now maybe we can go back to the presentation and.
Can we see a live? Yeah.
Yeah. Now we will see the live in
Another 6 minutes.
6 minutes. Let's say. Yeah. So here view presentation. Full screen.
Hey, students, seriously, if you are not interested, go ahead. Don't disturb others.
Now, you have drawn this, right? This 18 segments mirror. Why it's in the hexagonal structure? Why people have decided this hexagonal structure? Yes?
And it will help to zoom.
It will help to zoom. Okay, one good answer. Yes?
And easy to fold and unfold.
Easy to fold and unfold. That's another very good answer. Any more answer? Why it's in the hexagonal structure? Why not in a triangle or a square? Yes. Yes. Mostly it can be used as a, considerably it will be circle in shape. Okay? Yes, that's another good answer. Good answer. Yes, all the green answers are really good. And exactly the final answer, like the hexagonal structures, almost it will be looking like a circle, and it's easy to fold. He answered right. It's easy to fold. It's a origami structure. Okay. And one very important thing, I can introduce origami to you people. The origami is nothing but a science and maths. It's not just art.
Yeah.
You can play maths like anything with origami. Okay. You can learn maths with origami. How to fold, how to unfold. So these are all coming with origami structures. Okay? Yeah. So that's why people have built this 18 hexagonal segments to frame a mirror. And another beauty is we can even see if a square structure, if it is a square, some signals will be cut down from this boundary of the square. If it is, let's say this is square. If some signal is coming from a universe, some distant galaxy, it can reach this place, but it will be cut down because of the boundary, because it's a short boundary, right? There is no detector to receive the signal. But if it is a hexagonal, let's say this is square, but this hexagonal is having an extra part which can detect some signal, even some faint signal to transfer to the detector. Secondary mirror I told you, right? Okay. So some secondary mirror I told you, right? In the previous image. Maybe you can switch up the previous slide. Yes. So this signal, all the light will be received by this primary mirror, and it will be get reflected to this secondary mirror. From this secondary mirror, the signal will be transmitted to the detector. Here is the detector. Okay. So this, you have seen the TV dish, right? Dish TV and some direct HD. So dish TV. So similar like a dish structure, the primary mirror will receive all the signal. Okay? Yeah, next slide. 1 minute. Yeah. In a minute, we will go for we'll receive the image. Okay, so quickly I will tell about the mirror. Okay, this mirror, I told you, right, this is 6.5 meter length in a dia, and it has 18 segments. Each hexagonal segment is 1.3 meter in dia. Okay, so each segment diameter is 1.3 meter, which is made up of beryllium. Okay, so the beryllium is one material. You know, iron, carbon, other periodic table elements, right? So beryllium is one element in the periodic table. So beryllium, this mirror is made up of beryllium. The secondary mirror, I shown you, right? Here we have the secondary mirror. Okay, they need that one. Yeah. So this secondary mirror is having a 0.7 meter in diameter. Okay? Yeah, next slide. Okay, we'll stop now. We'll move to the.
Pay attention, no?
4 minutes exactly for the first shot.
So it's just 4 minutes to receive the light image. Now ours will be streamed.
Dreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search.
In the laptop live.
You can switch it.
We can't help it. A central element of new vision lies far beyond the earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal. We have uncovered wonders untruth. It's why our ancestors first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars.
No, I don't trust it really.
But we continue to search.
I think it send a signal moving around.
The central element
Time to catch up, no?
lies far beyond the earth.
Sound coming.
Why?
In the company.
It's okay.
Please read this again.
See the time here. In 2 minutes we are going to receive the signal.
So it's reducing, right?
Yes, it's reducing. Countdown, kind of countdown.
So let's count with it, okay? 2, 1.
Now, it's
We'll wait for it to reach 100 and then we'll go on down from 60.
Okay. Right, half the hour.
I'll say go, then you start from 60 reverse.
Okay? And together, no, you all come together. Enjoy the moment, you know? You're creating history, you're part of history.
Okay, 1 minute now. 21.
21.
Okay, now they will give some quick announcement and immediately they will move back to the actual image. So it's live now. Yeah, I think we have to wait. So we have still discussing.
This is it. This is the day we get the first science images back from the James Webb Space Telescope. And you've got a front row seat to the cosmos.
Right, little one.
Check YouTube wall in this
I'm Michelle Fowler, and the host what can only be described as a celebration for everyone on Earth. To think about this, life in the earliest days of the universe has been traveling to us for billions of years. Just over the last few weeks, we've captured some of that light with a telescope that sees the universe in an entirely new way. And today we share the very first results. So, long-time space fans have been making this. This is Dr. John Adler. He's the senior project scientist for the Webb Telescope and a Nobel Prize winner. And John, I couldn't be happier to be here with you today. How are you feeling?
To start something this big, you know, there's always a possibility. And it did work. We're so proud.
Well, you've been on this project for a very long time.
Started in 1995. We had just finished measuring the Big Bang. We measured it with the cosmic background explorer satellite that we built right here in Bangalore. We measured the spectrum. We measured the spots in the Big Bang. We said, now we know how it started. But then what happened after that? So then I got a call from NASA headquarters. Would I like to work on this new telescope that's going to help answer those questions? What happened after the Big Bang? How did the galaxies grow? How did the first black holes grow? What happened all the way from here to here. So this is our time machine, and I just wanted to be part of it. I'm so thrilled that we got a chance to do it.
One of the things that I remember saying this part of the music interview, after you win the Nobel Prize, you thought that this mission was the most important thing you did.
Absolutely. It's the big question. After you know how it started, what happened then? And suddenly we now have the technology to do it. We didn't have 50 years ago. We didn't have the technology 25 years ago when we started this. We invent things along the way, so we did that. And here it is.
Well, thank you. We'll be back to you in just a moment. So at the moment, we're going to talk about the way that Webb is a completely new way to experience. So today, the mission is the first science
That is the
image.
image.
It gives wings to the dreams
That is the
of
image,
so many
actually.
people who worked so hard for so long to make this possible. For everyone on Earth, this is your telescope.
Later.
This is the
That is
largest,
previewed.
most powerful
It already
observatory ever
launched
built.
by Biden.
It's the product of thousands of people working for more than 2 decades. This is a mission that's singularly focused
Yeah.
on the biggest
So,
questions.
yes, this is the image. Yeah, this image Okay, so this is a previewed image by Biden, the US president. He is previewed and he launched for the humankind. This is the first previewed image from the James Webb
It's
Telescope.
happening live, right?
Yes.
Simultaneously.
Simultaneously. It already, people have NASA have received already and they have transmitted now. So you can see some distorted structures here, right? I can maybe move a little bit zoom. Yes. You can see here, right, some distorted structures. They are actually very distant galaxies, far away from Earth. In front of those galaxies, some very heavy object is there. Let's say black hole. So those massive objects will bend the light. Actually, the light will travel in a straight line, right? We have studied in the classes. But these lights are carved by those massive objects. That's why we can see some curved structure. So this is called lensing effect, gravitational lensing. Due to the mass of very heavy object, let's say black hole, so those objects distorted the light, and these galaxies, actually this galaxy should be like a very faint, super image of galaxy. But due to the mass, heavy mass in front of the galaxy, So those lights got
I
distracted.
mean, in just one small section of what we are seeing.
Yes, one small section of.
Yeah, I mean that more than 50-60 galaxies.
Yes, see all the dots, all the light dots are galaxies.
Oh.
They are not stars. All the light dots are galaxies. Small, tiny dots. You can see.
So
See,
galaxies
star will be.
with their own sun, with their own
Yes,
planets. each
yes,
dot.
yes. All these dots, small dots are galaxies. You can easily distinguish between galaxy and stars. This is star because stars will have this diffraction pattern. Okay, some pattern we can see. So this is star, but all the tiny dots, which is not having this pipe kind of structure, are galaxies. So they are galaxies. Okay. Mugata, maybe I can just little bit okay, now you can see there are, in this area we can't see the distraction, but here alone, in this area alone we can see the distraction. That light has lens, right? Gravitational lens effect we can see here. Just zoom down, right? Yeah, in this location. Okay, so people are thinking like maybe in this location there will be a very massive object we couldn't detect in our naked eye, also in our infrared signal. So people are trying to observe this. Okay, so this is really fantastic, and maybe some more information we can see if we have analyzed inch by inch, pixel by pixel. Really, this image going to give so many research papers in the upcoming days.
Can we just focus, and is it possible from here to focus and enlarge?
Yeah, we can try little.
Virtual enlarge this part.
Yeah,
Just the image, let's see.
yeah. This is star. Actually, this is star. It has all the refraction pattern, right?
Right, so
This star. And maybe you can just slightly.
just go on here.
Yeah, here you can see that. So maybe some massive object in front of this galaxy. This is actual galaxy. So this light is completely distracted. So Einstein first discovered this, first proposed this gravitational lensing effect, but later all these space telescopes when we have built, we observe practically. But Einstein is the one scientist who first proposed this kind of gravitational lensing effect will happen when the very massive object in front of the larger distant object. Okay? Yeah. Yes. Yeah. All the tiny dots. This tiny dots. This is, you can see clear picture of actual galaxy. So this is bar galaxy. This is one type of galaxy in the universe we have. You can see some bar kind of structure here.
Yeah.
Some bar will be there and some spiral arms will be
One
there.
more below that.
Yeah. Maybe you can show one more. Some nebula is here. This is nebula, and these dots are galaxies.
Focus on the nebula.
Yeah. This one.
We can't go even
No,
further.
you can't. I know. We are not James Webb Telescope.
Mukherjee, you can try to.
Zoom is outside.
No. Just. Oh, that much.
Yeah, that's the
Oh, okay.
zoom limit.
Okay.
Where
Yeah.
are we? Like I said, we're not even a speck of sand. Inside,
Yes.
right? If you
Yes.
look at this.
Yes. So here see, some galaxies are getting interacting. So some galaxy will get merged. Two galaxies will get merged. Actually, our Milky Way galaxy is going to merge with the Andromeda galaxy. This is not going to happen in a day or month. It will take its own millions of years to get merged. Our Milky Way galaxy is going to tap with another galaxy, Andromeda, which is very close to Milky Way.
Andromeda.
Yes, Andromeda. Our Milky Way galaxy is going to interact.
What is this?
Yeah, they are galaxies. Yes. So this is a colored image, colored processed image. But when we receive from the telescope, we will like a very encoded, some encrypted information.
See, we're getting all this information now.
Now we go live
Right.
stream. Live.
So, John, a very inspiring experience. So it's kind of like a part of us.
In the live stream, it will take time because it receives already image
A
here.
very inspiring
And 1
experience.
minute
So it's kind of like a part of us that's out there.
because it's a direct stream, direct
million
mix.
miles away, part of our hopes and dreams are out there.
Already your images are all seen by NASA people. They have set the streams in the
No, they-
control room.
It's on
Now,
that side.
can you check your entry?
Also, otherwise, when you snap, just close it. Just close it now.
We can't see our children on the NASA website.
They should come in some sequence and call us out.
Oh,
I hope it's not too late. So they're coming one by one.
okay.
Close the plate,
Inspired experience.
So the entire world is observing this, right?
Yes, entire world is observing
Part of our hopes and dreams.
this historic moment.
So I'm just seeing as they
Yes.
look,
See
half the time the sun
the image.
and then
Little more,
we have
zoom.
because the
So all these distracted lines, gravity, lens effect.
our view of what's behind. And so there are these galaxies that look stretched and pulled, kind of like they've been magnified because they've been magnified by the gravity of the cluster, just like Einstein said they would. And it's really, there's so much detail here. We're seeing
So C is G, who is Webb operational scientist. I show the logo, right? Space Telescope Science Institute.
So we can look at it, we
From
can zoom in
that
on this image, and I encourage you as you grab this image at home, like zoom in. You can, really zoom in and play around. There are galaxies here in which you're seeing individual clusters of stars forming, popping up, just like popcorn. And then we also see in the background of this image, kind of littered like jewels all over the back of the image are these faint
So many galaxies are
red
there.
galaxies.
All the faint objects of
That is what
galaxies.
we built the telescope to do. The most distant stars are billions of years. We're seeing as they look more than 13 billion years ago. And so galaxies like that one right there, this little red guy, right? Yep.
So the one primary science goal of this, the scientific objective of James Webb Telescope is to observe the atmospheres of exoplanets. So our Earth is having exoplanet, right? Similarly, yeah.
Should I pause?
No. Okay, so here you can see some spectrographic image. See all these spectroscopic image will give information about what are the elements present in this particular galaxy, particular object. Okay, so they are showing that, right? So this object is having a hydrogen and oxygen, neon. So many elements are in the galaxies. I told you, right? We are made up of star dust. All the elements present in our bodies, even iron, calcium, all the elements, even carbon, this is made up of, this is woven in the core of some star. So that's why we are called as star dust. Okay? Yeah. So one primary scientific objective of James Webb Telescope is to observe what are the elements present in the extracelestial planet. That's exoplanet. Okay, those planets are not part of our solar system. They are part of some other sun, some other star. So they have their own system. Maybe when we are observing the atmosphere of that particular exoplanet, we may know if there is some extraterrestrial intelligence, alien. So this James Webb Telescope may give some information about the alien.
Research for exoplanets wasn't even
So let's wait.
Exploring exoplanets.
Because atmospheric studies will give some
Second
information.
by second, they revealed the day.
Yeah.
And they sent it down to our friends, Natalie.
Okay. So we saw the first image of beautiful image of James Webb Telescope, and we will get surely people will observe and they will detect. So many science publications surely will come in a month or a year, let's say some quarters. We will get some information about the distant galaxies. Yes. So we discussed about the mirror, the scientific information. Next slide. Yeah. So these are the four primary targets right now. These are the four primary targets for the James Webb Telescope immediately. So one is Stephan's quintet. So this is group of galaxy. So this Stephan's quintet is going to observe by James Webb Telescope immediately after this first image we have received, right? So now people are going to align the telescope and in a specific direction. This object is in Pegasus constellation. So Pegasus is one constellation. Yes. So Pegasus is a constellation. So we have in so the constellation is nothing but a arc kind of structure. We have connected all the stars. Sorry?
Images,
Pegasus?
Yeah, you can see. So the Pegasus constellation.
Yeah.
Just search Pegasus constellation.
Constellations have got different shapes, no?
Yes.
So sometimes the names.
So this is an imaginary structure. We draw. There are stars in the sky, right? We just connected each stars, and it's looking like a horse. It's looking like a spoon. Yes. Yeah, that is. Maybe you can show this picture. So almost all the constellations nowadays, it starts looking exactly in the graphic structure. They distorted, somehow they distorted. The only one constellation we can see in the exact structure is Scorpius. Scorpius is the constellation. You can see the scorpion structure in it. Okay? So in this Pegasus constellation, we can see that Stephen's quintet. Okay? They are group of galaxies in a very narrow region. So usually this group of galaxies will be in a wide range, but Stephen's quintet is a very narrow area. So that's why James Webb Telescope is interested to observe that. What is this galaxy cluster? So they are not a stars, they are galaxies in a very small region. They have clustered. Now we need to understand what is the element is contracted all these galaxies in a smaller region. So James Webb Telescope interested in it, and maybe you can show the presentation. Yeah. So another one is Southern Ring Nebula. So this is Southern Ring Nebula, which is it is located in the southern hemisphere. In yours, we can see in the southern hemisphere. This is Southern Ring Nebula. So this is central star. One star in the central, it died. Actually, this star is died. It exploded. The supernova happened. So it exploded in a way, and all the gas elements present in that star are moving away from the star. Okay, so it's moving in all the direction 9 miles per hour. In an hour, all the clouds, all these molecules are moving 9 miles per hour. In an hour, it will move 9 miles. Sorry. So this is one interested target for the James Webb Telescope, Southern Ring Nebula, and another is Carina Nebula. So you can see this Carina Nebula. This is very complex structure. We didn't see such complex structure in the universe. That's why James Webb Telescope. What is this? Why this complex structure is there in the universe? So we are going to observe this complex structure, and this SMACS 0723 is this. I showed this distorted structure, right, in the previous image, James Webb Telescope first image. So this is galaxy group of galaxy. So they are very massive. They are forehead, very close to our body's solar system. So we want to observe why this distraction is happening here. So this massive object, massive cluster, we are going to observe using James Webb Telescope. And WASP 96b is a exoplanet. This is exoplanet. Okay, WASP 96a is the star. So here A will count. That is actually the star. So we are going to observe that star's planet. Our Earth is having a planet, right? Various planets, Mercury, Venus, Earth. So similarly, WASP 96b is the star. Our star is Sun. So we have named that star as WASP 96a. So that star is having a planet. That planet named as 96b. Okay, so this planet, the exoplanets, James Webb Telescope is going to observe. So another primary objective to observe that, to detect what are the elements present in the exoplanet, atmosphere of that exoplanet, 96b. Okay, so these are the four primary targets right now, immediate after this first image, James Webb Telescope going to observe. Okay, yeah, move on next image. Yes, so this is the science goal. James Webb Telescope will be giant leap forward. I already explained this. Our quest to understand the universe and our origin. So we are going to observe the biosignature of early universe. Yes. Okay, so we will examine every phase of cosmic history from the first luminous glow after the Big Bang. I told you, right? So after the Big Bang, we didn't have any light. After Big Bang, there was no light. It was completely dark. Because there is no stars to emit light. Because there is no galaxies to emit light. There is energy. There was energy. the energy is not allowed to the capacity to emit light. So we need some object, right? So first stars form, then galaxies form, then we have the light. So this James Webb telescope is going to detect the first luminous glow after the Big Bang. So we are going to detect that. So that's why this James Webb telescope is very super duper telescope. And we are going to see some star formations and galaxy formations and planets and their atmosphere, also some biosignations of our.
So would you say in observing all this, we finally come to know how we happen?
Yes. Yeah, there may be answer. We are expecting that. All the scientific communities are expecting that answer. Yes, we have a hope. Surely we will get some idea about the light formation, origin of light, let's say.
So Mukunda,
Yeah, so thank you very much.
Is that ready? Please sit down, everyone. Thank you. Please sit down. I'm waiting, child. Please sit down. Thank you. 1, 2, 3. You've been very patient. You are excellent listener. No problem. Yeah. Okay? You are listening very well. Of course, there were few, were a little distracted. But the next session that we have, I'm sure only those who are interested will come. Okay?